As we said, my name is Doug Finkelberg, Area Extension Educator, and I'm presenting on behalf of Dr. Kurt Schroeder, who is not able to be with us at this morning. Last minute, things popped up. Kurt was unable to join us. So he was gracious enough to have completed his presentation ahead of time, which I'm very grateful for. And he was kind enough to share it with me. So the slides that we'll be seeing, the research that we'll be discussing, much of this has come and filtered through Dr. Schroeder's lens, and he's compiled these. So moving along with our introduction and overview to set the stage of why we care about soil acidity in the Pacific Northwest and why we're all here for this. First of all, we need to discuss or understand that pH is what we're going to be talking a lot about today. It's the negative log of the hydrogen ion concentration, which doesn't tell us much. What it really is a measure of the degree of acidity or alkalinity that we experience in the soil solution. We commonly see it represented on a scale of 1 to 14 or 0 to 14. It's a log scale, so each step of the scale is a 10-time change. Kurt has put together a nice illustration of what that might actually mean, where we see that where pH of 7 is our neutral point, and that each unit we move away from that is a 10-time change in either acidity or alkalinity. So what we really want to take away from this, our understanding, is that a small reduction in pH is actually a very large increase in acidity or that hydrogen ion concentration. And we can see that as we go all the way from 7 to 6, 10-time change, 7 to 5, 100-time change, 7 to a pH of 4, we've got 1,000 times more acidity there to deal with. This has direct implications for how much effort or neutralization it might take to get us back once we're down at a pH that is such an extreme situation. So what does that pH scale, how can we conceptualize it from a real world standpoint? If 7 is neutral, we think of waters commonly being a fairly neutral solution. Milk is fairly neutral. Rainfall collects a little bit of acidity as it falls. It becomes slightly acidic. Coffee, beer, some of my favorite things, they're down about a pH of 4. As we start to get to the extreme ends of battery acid, that's where we're at our most acidic. In the opposite end of the spectrum, we might be up to bleach or sodium hydroxide, things that are incredibly caustic or alkaline. When we're talking about what this means in a soil environment, our prairie cutover or our prairie soils are slightly acidic, and naturally our forested soils are slightly more acidic in that 4 to 5 pH. And then say Southern Idaho soils in a different environment, they're going to be calcareous and they're more on the alkaline end of things. Unless we're in central Washington, unless we're in central Oregon, most of the area that we're discussing here today is going to fall into this neutral to naturally acidic soil environment to begin with. So what are the processes that produce acidity or hydrogen ions? Plant growth, organic acids being pumped out of plant roots, just the accumulation of organic matter over time, nitrification, or the oxidation of nitrogen to make it into a nitrate form. Similarly, oxidation of sulfur can result in soil acidity. When plants uptake nutrients in the cationic form, we have an offset where acidity is produced in the soil. And then we have fertilizers that can cause acidity in soils. In particular, some of our phosphate fertilizers can be very acidifying, as well as sulfur and some other nitrate forms. So nitrification is something that we talk about a lot. It's essential for changing ammonium ions into nitrate ions, which are plant nutrition. This is a bacterially mitigated process, which means it doesn't happen without cooperative bacteria, and it occurs most efficiently in well-aerated, moist, warm soils. So this is when we start seeing nitrogen become available in the late spring, early summer. It's largely nitrification processes at work. It's important because it takes bacteria, it takes happy bacteria to be efficient and full for the process to go more fully. And we'll see how acidity can be a counterproductive weight on the efficiency of nitrification to occur. So why do we have low soil pH in the Pacific Northwest? We've got a 70-year history of using ammonium-based fertilizers, and that has produced acidity every year that they've been applied. So we've got soils that were, some of them were already in a more acidic form than others, such as our cut-over timber soils. They also were less well buffered to begin with. And I know that buffering is a topic we'll get into later in the presentations, but what we want to understand is that we already started from a slightly to a more acidic standpoint, and we've just pushed that needle further on through the use of our ammonium fertilizers and cropping practices. Is this problem exacerbated with direct seeding? As in, as we see a difference in our cropping system practice with our tillage? Well, we don't actually see more acidity, and we'll go into it in a little more detail, but we do see some stratification of that acidity being more pronounced with direct seeded systems. So we'll touch on that a little later in this discussion. So where were those soils that were a little less well buffered, a little more acidic, historically forested soils located? Throughout much of North Idaho, throughout some of eastern Washington, southeast Washington, north central Oregon, northeast Oregon. So these are the areas where we're going to expect to see a lower starting point on our pH or a higher starting point on our acidity to begin with. Now, how do we offset acidity? We're probably very familiar that the use of agricultural lime is the key accepted practice for raising soil pHs. The application of ag lime has been a common agricultural practice throughout the globe for a long time. This area happens not to have a lot of readily available lime deposits, and so it has not been as regular an employed practice. But when we're talking about how much acidity do we get from the different that we use, it's important to know that they're not all the same. Some have a greater acidifying potential than others do. And one way of understanding that potential is understanding how much lime would be required to offset the acidity created by the fertilizer. So in this chart, we can see the lime required to neutralize soil acidity produced by common fertilizers, such as anhydrous ammonia, urea, ammonium nitrate. These sources all have a equivalent amount of lime that would be required to neutralize them. And we can see in comparison that when we get up to products like ammonium sulfate or MAP or DAP or monoammonium diammonium phosphates, they are much more acidifying in a unit per unit basis of comparison. Interestingly enough, TSP is applied in a form that doesn't affect soil acidity. So when we get to the point where we're talking about mitigation strategies, one way to start out from a point of not increasing acidity would be to find a phosphorus source like TSP that doesn't add so much so quickly. So let's visualize this in another way. Back in the 80s, soil scientists from the University of Idaho, Bob Mahler, did a lot of the original work in characterization of soil acidity and its implications across PNW and North Idaho in particular. One of the experiments that they did was they added 120 kilograms per hectare of nitrogen at 21-day intervals. And that's 100 and a few pounds of nitrogen per acre, if you want to translate that to units we're probably a little more familiar with. So what they found was that in the soil they were working with, after 10 additions, 10 cycles of a little bit of over 100 pounds of urea being added, they could take the soil they were working with from a near neutral or slightly alkaline standpoint and shift that pH all the way down to mid fives, upper fives. So an analogy might be 10 cropping cycles at this, with this soil and this fertilizer application rate, you can already see a large shift in soil pH. We want to take a more acidifying fertilizer like ammonium sulfate. They did the same experiment and they found the same results. They just achieved that level of acidification in fewer cycles because this particular formulation of fertilizer produces that much more acidity, and we see it reflected in the charts here. So what does this look like from a landscape level? If we look across the Pacific Northwest and we look at soil tests that were taken in the 60s, 70s, and 80s, Mahler produced this chart that's somewhat famous for those of us who geek out on soil acidity issues that shows this steady decline of soils showing up below a pH of 6, where the majority of them were above pH 6 in the 60s, and we see that decline steadily occurring. And guess where we see it occurring first? In those cutover timber dominated soils where we know they're more poorly buffered to begin with. They already started at a lower pH. So this is following what we would expect to occur. But what this shows is this for 20 years of farming practices, the addition of industrial fertilizer in the forms that we have available and that we use, we saw we could measure a decline in regional soil acidity, soil pH, an increase in acidity. We'll look at some hard numbers. These were 6-inch soil samples. So we're talking about the top 6 inches of soil. That's the area where we tend to see acidity accumulate. And during this time, there was a bit of a bell curve between pH of 6 and 5, with the majority of samples being somewhere up around pH 5 or 5.5 or above, 5.4 or above. So that's where the situation was at in 85. Dr. Schroeder and I conducted a regional soil survey in 2014, 2015 to try to update Mahler's map, or at least Idaho's portion of what was represented in Mahler's map. And to do that, we partnered with Tabitha Brown, who was with the Latah County Conservation District at that time, and we pulled soil samples from Kootenai, Benoit, Latah, and Nez Perce, Lewis, Idaho, and Clearwater counties, and collected about 116. Most were from annually cropped ground, 11 pastures, 6 CRP, and a couple of native soils for comparison purposes. And so here's what we found when we updated, or we tried to update Mahler's map, is that 77% of the samples that we collected were actually below the average of what Mahler had found in his representation from the 80s. So we characterized a continued shift downward in pH, or continued increase in the accumulation of soil acidity occurring in the farmed environment of the inland Pacific Northwest, or North Idaho in particular. And this will have some implications for, well, we'll discuss this a little further as we move along, but we can see that as time has gone by, as we would expect, the continued addition of the fertilizers that we use, we continue to add that acidity, and we continue to see it reflected in the soil samples. So this was almost a decade ago now. It's almost time to do the study again and characterize comparisons. But this is Idaho. What's going on in Washington? Well, Paul Carter was with WSU Extension, did some excellent work with the application of lime and micronutrients, and in this zone, or in this area of interest. We also did was he put together a great comparison of soil samples taken across a whole bunch of sites in southeast Washington. And it basically tells the same story, where you have soil pHs wavering from 5.5 to 4.5. The median is somewhere around 5, very similar to what we saw. A few outliers, there's always a few outliers that occur, but when you compare it to the native soil pHs, they are spot on, near neutral to slightly acidic, which is what we would expect from this environment that had not been farmed and fertilized. And so this slide just helps represent that what we are seeing in Idaho isn't anomalous. Those same practices are employed in Eastern Washington, the same results are being observed. So let's talk about stratification. Where within the soil profile is the acidity? Dr. Schroeder, when he was establishing what's a now concluded multi-year research study into the application of different liming products and rates and crop rotations here in North Idaho, and Eastern Washington, did some detailed characterization of soils that he was working with at the beginning of his study some years ago. So there was a tilled site in Pullman, Washington, and a direct seeded site in Winchester, Idaho, where he took 60-inch soil cores, and then on a centimeter by centimeter basis, or 2 centimeter by 2 centimeter basis, he characterized where the acidity was at within that core. And what we find is that both the direct seed and the tilled sites showed the same trends, but in a little different way. And I think this helps us understand the difference in how we observe acidity in a tilled system versus a direct seeded system. What we find is that the most acidity doesn't accumulate in the top 2 inches. It actually accumulates and shows in the 3 to 4 inches. Why is that? Because that's where we put the fertilizer, and that's where the chemical reactions occur. It's less pronounced in the tilled ground. Why? Because that soil's mixed, and so the effect isn't as acute in the zone, but you still see that inflection in that 2 to 6 or 2 to 10 centimeter zone, or that 2 to 4 inches. We see it more pronounced in the direct seeded, but what's interesting to understand is that once we get below 6 inches, the pH starts going back to native or regular pH of what the parent material held before we started manipulating it. So where's the acidity located in these soil profiles? Near the surface, not at the surface. So where do we want to correct the pH if we can? Well, it's going to have to be within that top 6 inches, but it's not on the surface, it's within the profile. So some editorialization on my part. So we have a stratification of pH. We've got soils that are increasingly acidic, lowering in pH over time. What does it look like between the fence rows? Is it a continuous amount of acidity, or do we see changes within the fieldscape? And we sure see a lot of differences within the fieldscape. This work comes from Tabitha Brown, again, who was with the Layton County Conservation District at the time. She was doing this work as part of a characterization study. And what we're looking at here is a 100-acre field, and we're seeing a pH map. We're seeing wide variance of pHs. Down the center of the field, we see the lowest pHs, and then as we go across the field, we see a row of fairly high to neutral pHs. Why is this? Because this is where at some point they pulled a fence row, made one 40-acre field into 2 or 2.5 fields to be 100 acres, and we're seeing the historic remnant of non-farmed fence row that still is showing up all the years later. This is now just farmed as one unit. So land use practice, movement of soil, we can see a lot of variability within the soil, which is why I'm really excited to hear Joaquin Casanova's discussion of how to use aerial imagery to help create this type of understanding of where acidity is at on the landscape, because prescription application may become one of our more economical solutions down the road. So why are acid soils a problem, right? Like, why are we here today talking about this stuff? Because soil acidity, pH is a master variable, they say in our chemistry classes. Soil acidity impacts all the chemical and biological processes that we're particularly interested in, such as nitrogen use efficiency, which acid soils have a reduced amount of, nutrient holding capacity, nutrient availability, calcium, potassium, magnesium, molybdenum, all of which can be negatively impacted. Phosphorus can become less available. Aluminum toxicity, which we'll go into, can become a nightmare in some places, depending on the level of acid that you have. We see reduced biological activity, translate that to reduced nitrification. We see the toxicity to rhizobia and legumes, impacts on plant diseases. And in our arid environment, we see some of our herbicides, especially our group 2s, become much more persistent, and then rotation becomes more problematic, and we start having other legacy effects. So the soil acidity really has an outsized impact on almost every step of our cropping system in the PNW. But let's dive into pH and nutrient availability for just a minute. This is a widely seen chart by Tro and Wegner. And what this is showing us is some key macro and micronutrients and how available they can be to plants as you shift across a very acidic to a very alkaline soil environment. And the takeaway is that most of our nutrients are most available when we're near neutral, and the more we deviate from that, the more problems occur. We can conceptualize this another way by looking at soil pH and the amount of fertilizer that can be available. So this is taken from Paul Carter. Thanks again, Paul. What we see is that as we are in a more acidic environment, the amount of nitrogen, potassium, potassium, phosphorus, we're underutilizing, or we have to apply more to achieve the same results. And so having a very acidic soil is very counterproductive when we talk about nitrogen use efficiency or getting more out of our inputs. If we want to reduce our input costs, addressing soil acidity is going to be one of the ways that we can get there. So how does this occur? What's what's going on the chemical level? Soils have a net negative charge. They have a net negative charge characteristic because they're made of clay silicate minerals. They've broken edges that create that negative charge. Thank God they do, because they capture cations, especially the ones that are the nutrients that we want to have for our plants: calcium, magnesium, potassium. Unfortunately, when we have more acidity, the hydrogen ions come in, they kick off the nutrients the cations grab anions. Hydroxide would be fine, but they actually grab nutrients like sulfate and nitrate, and they can wash out of the soil profile then. So acidity can displace our nutrients and lead to their being leached from the profile. Not very efficient fertilizer usage. Another aspect that I mentioned earlier was aluminum toxicity. So when we are looking at that Mahler produced data in our subsequent survey across northern Idaho, we didn't just look at pH, we also looked at available nutrients and the metals. And what we found is that as we get to about a pH of 5.2, we start seeing measurable soluble aluminum. And when we start getting to 5.1 and below, we start getting appreciably increased amounts of that soluble aluminum. That has some real negative effects on plant growth. We'll get into that here in a minute. But it's good to understand that there's something going on when we hit that 5.2 to 5.0 mark, where not only do we see increases in biological function, we're now liberating aluminum, and that just by itself puts downward pressure on plant productivity because it's a toxicant. So when we did the survey looking across northern Idaho, we tested prairie, native grass, grass hay under production, CRP, and annual cropped ground. We have a wide range of pHs. Where we saw the aluminum was almost entirely in the annual cropped ground. One in the grass hay, but that was a field that was under production historically and had been regularly fertilized for a long time. I believe that was also up in Kootenai County, where we have cutover timber soils, poorly buffered to begin with. So where we didn't see it, CRP, native forest, those are not being fertilized so heavily, not being farmed so heavily. So what's the relationship between pH and toxic elements? We talked about how as we get lower in pH, we can liberate aluminum. Before that, we're starting to see a lot of iron and magnesium come into solution. At high enough levels, they can become toxic to plants, although I don't know if we've documented manganese and iron toxicity. We can definitely see aluminum toxicity. It takes a lot less aluminum to cause a problem than it does with iron and magnesium if you look at how many parts per million. Why is that? Despite being one of the most abundant metals in the Earth's crust, at about 70% of the Earth's crust, aluminum is largely complexed in ways that don't make it plant available, unless the soils reach an acidic enough level that we can start peeling some of that into solution, start dissolving some of it. And then that soluble aluminum, or the Al3 plus, is the form that it's in. It attacks root tips, it affects hormone signaling, and it interferes with calcium uptake. And it causes healthy roots to start looking like this: stubbed, clubbed, and with a lot fewer root hairs. What does that look like in the natural environment? Here we have a healthy, happy Alicat spring wheat that has root hairs, and those root hairs grab a hold of soil and are able to hold on to it. And then we have the aluminum sensitive scarlet spring wheat that has a nice, clean, root hair free type of clubbed root system that is not going to be for nutrients or perform efficiently, and certainly will not be producing the volume of grain up top that its neighbor, the tolerant Alicat, will. So aluminum can have severe effects. What does this look like on a landscape scale? These are next series of pictures will be taken from Rockland, Washington, or from that area. Cut over timber, history of bluegrass seed production. Bluegrass seed is a production system where you pour on the nitrogen to year after year, and it's a perennial system. So they tend to acidify very quickly, especially if they start out in a poorly buffered environment. Here we see a spring wheat field that isn't surrounded by more green things. The reason is because this field has a low enough pH that there's soluble aluminum. Up close, it looks like this, which we don't see a lot of tillering. We see plants that have gotten 18 inches maybe and are struggling to produce a seed head. When we look at some other fields, we might see more of a patchy nature. Tend to see acidity accumulate in one portion of a field over another. It's more to do with the use, the application history, and how soil may have moved, but we tend not to see it accumulate in the low spots or accumulate in the high spots. So that can be difficult, but it does help us differentiate, say, nitrogen deficiency from, which we tend to see in waterlogged soils in spring, say, in low-lying areas, where this might show up on the hill slope as well. And here we have a picture of hill slopes with patches forming in it. You go out there and you test those, and those spots are going to have lower pH than the surrounding areas. Again, characterized by thin patches, non-thrifty plants, not tillering, just sorry looking characters. But you're not going to find other disease presences. This is not a disease caused. This is a toxin caused plant reaction. So what do we see because of aluminum toxicity? How do you identify this? Reduced tillering, reduced seedling vigor, yellow stunted plants, patches occurring anywhere in the field, not just in one place or another, which helps you differentiate it from a nutrient deficiency. Then we've got the plant sensitivity. Symptoms are going to be most obvious in more sensitive species like barley, peas, lentils. And in severe cases, it can take a whole field. In less severe cases, where we're only flirting with some aluminum being available in places, you may only see a subtle reduction in yield until you get to the tipping point where it's much more available. So I mentioned that different crops react differently, have different tolerances of acidity. We can look across the commonly grown crops in our region and see that some of the most tolerant varieties of crop we grow, wheat, barley, peas, are oddly enough ones we grow most commonly. Most susceptible, though, are mustards and canola, alfalfa. These tend to have more of a sensitivity. Chickpeas, Kurt lists it as questionable. I think that's because there may be more of a variety interaction with chickpea tolerance that I don't know if we've completely understood yet. But just like with wheat having tolerances, we see more of a spectrum of susceptibility. So how do we understand where these pH thresholds are? We can go back to McDowell and Mahler's work from the 80s, where they acidified soils and they took plants to yield in pot surveys. And what they found, and that's pots as in pots in a greenhouse. And what they found was that when they started to find the inflection point at which pH you saw a serious decline in yield, they called that the point where the crop was sensitive. So in this case, that's how we get 5.2 for winter wheat. It's how we get 5.6 for lentils, in the same scenario for peas. We want to look at crop tolerances to acidity or aluminum toxicity. Another way to represent it would be to look at most to least tolerant. Most tolerant is going to be triticale, then wheat, if it's a tolerant wheat, timothy, canola, chickpea, wheat, mustard, barley, pea, lentil. This is a slightly different scale than what Mahler had published, but again, I think that we have to understand that varieties change over time and varieties have their own range of tolerances. And I think we might see, who's third or fifth being represented in some of that tolerance by variety interactions. Which crops are just the most tolerant to aluminum in particular? And this may be important for some folks trying to put, say, cover crops into a really acidified environment. Well, bad news for the wheat export industry, but buckwheat is very tolerant to acidity. Oats are a crop that are very tolerant to acidity. So is rye. Really, please don't go buying a bunch of Italian rye out of the Midwest for cover crop purposes and bringing it up here. We have plenty of our own, and it's a weedy species, and it's a huge problem in our cropping systems. But it's very tolerant to acidic soils. Again, go figure. Lupins, potatoes, corn, also very tolerant to soils that have free aluminum in them. And then, as you might expect, plants like blueberries that thrive in a very acidic environment are going to have their own tolerances. So no real surprises there. But let's take a look at what this difference in tolerance can appear like in a field. In this image from the Palouse, we have a winter wheat variety that has susceptibility that's probably on the more 5.4 or above is where it's happy, and not happy below, with a winter triticale. And winter triticale, as we just saw, is the most tolerant to aluminum in the soil. And I think this picture goes a long ways towards showing how tolerance by species, tolerance by variety can affect in-field performance and success if we have this acidified environment. So plants are not the only thing affected by acidity, although we've just seen some images that really, I think, should drive home how affected plants can be. We also have soil microbes that are affected. And the long story short is that as we see lower pHs or increasing amounts of acidity, we see a shift in the spectrum of microbes. We see fewer of the bacteria that want to be involved in the nitrification process. So we see less nitrification as we get more acid in our soils. We see a shift in funguses. So we start seeing less mycorrhizal fungus and more pathogenic or problematic funguses to many of our crops. Let's see, below 5.8, most beneficial bacteria are inactive or diminished, and fungi, particularly pathogenic fungi, have tended to increase. So there's a number of reasons why that occurs, but that is the effect that we see. And another consequence of soil acidification is a shift in the microbe herds under the soil to deal with that acidified environment. And the translation is it results to, again, hammering this home, less nutrient efficiency, or less efficient nutrient cycling. A lot of that comes, and more plant disease coming from that increase in acidity and the shift in biological populations. So how are fungi affected? How are the funguses affected in the soil? So the pH affects the ability of fungus to take up food, and that can influence the amount of trace nutrients that can become available. Then we have low pH distressing plants in general, which can make them more susceptible to the increased fungal populations that are ready and willing to take advantage of now stressed plants. So low pH can reduce the natural populations of microorganisms that might normally suppress some of our pathogens. Let's take a look at the top two in low and high rainfall areas. We'll start with the high rainfall first. In wheat, we're particularly concerned with sea stripe or cephalosporium. Here's some images of cephalosporium graminearum. Winter wheat, this is our high rainfall zone. Here's some work from Stiles and Murray. We're going to be hearing from Dr. Tim Murray in our next session. And he'll go into some of these interactions in much greater detail. But the Cliff Notes version is, as pH decreases, increase in disease incidence goes up. And a number of studies have supported that. And Tim can go into much greater detail, especially when you get into varietal interactions and other things. But that relationship exists, and we need to understand it. In the drier areas, the wheat fallow or the transition zones where we're looking at 14 to 18, 19 inches of precipitation. Sea stripes, much less of an issue, but don't worry, you've got your own pH-dependent pathogen, Fusarium crown rot. And we tend to see more Fusarium crown rot in these soils that are pH stressed or stressed with low pHs. And it's exacerbated by high nitrogen rates, and high nitrogen rates become increasingly necessary the less efficient the soils can help nutrient cycle. And so you start seeing a deleterious cycle or can occur. So influence of soil pH on Fusarium crown rot research has shown that ammonium fertilizers increase the disease incidence and severity, and that this is a similar response observed with Fusarium wilt diseases on other crops. So again, I'll let the pathologist go into greater detail, but for purposes today, we need to understand that it's not just nutrient cycling that's affected, but plant diseases caused by fungus can be augmented and increased and influenced by our acidic soils. So just another reference to the research, we're seeing that soil pH inversely correlated with the quantity of nitrogen implied when we have a lot of Fusarium crown rot to begin with, so driving home this three-way interaction between acidity, nitrogen use efficiency, and plant performance. So I've got about 15 minutes left here, and we'll take this on into a soft landing. What do we do? Or what has been being done, I think, is a good way to start wrapping up this very quick romp through the situation in the Pacific Northwest. One way, and one approach has been to try to select for varieties that are tolerant to the situation. So it's kind of a stop the bleeding approach from my editorialization. So a single gene has been identified in wheat that can provide tolerance to acid soils. And it's a gene that regulates malate, and that malate binds with aluminum, free aluminum, and keeps it from harming the plant root, keeps the plant from having to take it up. There's a cost to this to the plant, and in soils that aren't pressured with high acidity or an aluminum toxicity, this variety or varieties with these genes tend not to perform as well as other wheat varieties. But when that pressure exists, these varieties will make seed, whereas we saw in some of our other pictures, more sensitive varieties might not even get that far. So breeding for aluminum tolerance is a option, and it's one approach that is being done, but it has a cost, and that cost is a lower top end yield potential. There are some other mechanisms of tolerance that we believe exist but don't fully understand, and I'm hoping that when we get to our in-person day on the 18th, this is one of the many topics we can explore, is where our breeders and other researchers are in identifying other mechanisms of tolerance. So one of the things that Dr. Schroeder's program is doing at the University of Idaho on the Moscow Research Station at the Parker Farm is screening for aluminum tolerant wheat varieties. And this means is that plant breeders from across the region are sending early generation material or material that hasn't necessarily been released yet is in consideration. And Kurt is planting hedgerows of this material in a field that has a very low pH, as free aluminum, and is an excellent place to screen for varietal adaptation and performance. And so here we have different hedgerows of wheat being grown, and we can see the varying levels of tolerance that they have. This information then gets conveyed back to the plant breeders, and they can help them. It helps them decide whether to advance lines or to understand the full spectrum of varietal characteristics that a line might have. I think that this is a critically important service that Kurt's providing to the regional wheat production process. So what do we do with acidity? We mentioned before, liming has been understood to be the key way to raise soil pH or to neutralize acidity. It neutralizes toxic elements, it drives that aluminum back into the solid phase, decreases manganese. Obviously, once we start raising that pH, we start unlocking the benefits of having a near neutral soil environment, which is better nutrient availability, better microbial activity, the presence of more micronutrients, the potential for them to be available. How does it do this? Lime is calcium carbonate, magnesium carbonate, some combination of the two, and they, well, as we can see in this graphic, as you add that calcium carbonate, the carbonate attaches to the hydrogen, calcium displaces it off the soil colloid, we end up with water and CO2. In the case of aluminum, it goes back into the solid phase by complexing with hydroxides. So back to the Parker Farm, and that's our North Idaho, University of Idaho screening site. Years ago, Kurt put 5 tons of liquid lime on a portion of this field to create some replicates and be able to have an environment in which to do experiments. The pH was 4.2 to begin with in that upper 6 inches with over 50, maybe even 100 part per million, if I'm recalling correctly, as an appreciable and impactive amount of soluble aluminum was present in these soils. These soils are well enough buffered that it took 5 tons of lime to raise that soil pH back into the closer to a pH 6 environment in which you could get this barley crop to grow. The same crop was planted in the no lime section, and it can't grow because it's sensitive to aluminum. And here we see a great example of what that looks like. But it took 5 tons to get it there because it was so acidified in the first place. So think about those numbers for a minute. Which gets us to the point of understanding buffering and the soil texture interaction. I'm going to briefly gloss over this because I know it's going to be discussed in much greater detail, but the more clay a soil has, the more acidity it can soak up, the more lime it's going to take to neutralize versus a less well buffered soil that would have more sandy texture. So we might be looking at, depending on buffering capacity, a wide spectrum of application rates to achieve the same result. So how do we look for acidity? Where do we go to find it? We're talking about sampling the upper 6 inches of soil because that's where the fertilizer is applied. We want to take multiple samples from a field because, as we saw, variability is very large across that landscape. The KCl extractable aluminum, you might hear that phrase, that just refers to the lab process that technicians use in order to determine how much aluminum is present and plant available. Because remember, there's a lot of aluminum in the Earth's crust, very, very little of it, if any, is plant available. So this KCl extraction process lets us understand how much aluminum might be there. Soil tests let us know cation exchange capacity, base saturation, the other characteristics we need to understand, as well as soil pH. You can't tissue test for aluminum. I know tissue testing has become very popular, but it's not the test that's going to give you the information you need from an aluminum toxicity standpoint. You need to have a soil test for that. And then lime requirements, this is the number a lab might give you to tell you how much of what kind of lime might need to be applied to achieve some target change in soil acidity. And Kurt's comment is not, this is not a particularly reliable, there isn't a particularly reliable lime requirement test in the PNW. I'm very excited to hear Carol's addition to that comment, or her repost, because I think that's where we may be going next. So in summary, I appreciate everybody sticking with me through this sort of whirlwind overview. Soil pH has been declining in the Pacific Northwest for 70 years because we put fertilizer in the ground. Specifically, we put ammonium fertilizers as a regular part of doing business to feed our crops. And the consequence of that, in the absence of any liming, has been a continuing decline in soil pH. The number of fields affected by acidic soils are growing, and the acute symptoms of toxicity are showing up in fields on cutover timber first. It's where we would expect them to. So land use pattern is important, understanding where the most problematic things are going to be first. Potential solutions include what I think is Band-Aid solutions, but aluminum tolerant varieties, tolerant crops, and then what we're going to get into a lot more, liming. So strategies to minimize soil acidity. These will be discussed in greater detail, but avoiding excessive nitrogen fertilizer application or increasing your nitrogen use efficiency is thing one. Practices that increase nitrogen use efficiency are key. Variable rate nitrogen application or using technology to more accurately pinpoint and utilize that nitrogen is going to play an increased role in this. Diverse crop rotations that don't require as much nitrogen in the first place, just legumes or barley, can help us stretch out the amount of time that we have before we've acidified the soil as much as if we were in just a wheat on wheat rotation, for instance. If we can avoid removing residual or residues, the baling and burning is a way to really speed up soil acidity accumulation. And the opposite of that, which is the addition or maintenance of organic matter in the soil, has the opposite effect and is a great way to preserve cations and increase buffering capacity. So it's a big challenge. It's an issue that's affecting a wide landscape, and it really is putting downward pressure on efficiency and productivity. And I appreciate everybody spending time to go with me through Dr. Schroeder's slides. So with that, I'll quit sharing and we'll see where we're at.